Good morning, everyone. So I decided to make a fresh video just to start off where we left off so we could just continue our lesson. So as I discussed in class, we're going to move forward with speed and velocity. I'll show you one detailed example, and then I'll talk about constant motion because our next topic is going to be non-constant motion, or known as acceleration. So I'm going to jump ahead to this slide right here, and just like I advertised, there are a few types of motion just based on the way we measure it. So there is the scalar quantity and there's the vector quantity. So our scalar quantity is speed, just like I described. So a speedometer in your car measures speed because it only tells you how fast you're going, like 25 miles per hour. Velocity is how fast you go in a particular direction. So that's if you had 25 miles per hour north, if you knew that piece of direction as you drive on 91, for example. Now, in physics, we always use the symbol V for velocity. And then usually, you either use S for speed, or you can use, sometimes we interchange speed and velocity with V, but just know that the more common symbol we're going to use is V for velocity. So, just as I explained in class, average speed, for example, or speed, well, I'll just start off with just speed. Speed is distance over time. So what we're doing is we're taking the total distance and then dividing it by the time. Now, the average speed of an object is going to be the total difference of the total time. So just note that when I talk about average speed, that can change over time. So it's exactly what you might imagine. It's the average speed. It's the speed that you're going on average, not a speed at any particular moment. So this is just a really fancy way of showing that. Actually, I have my little fancy thing here. Here we go. So this is just a really complicated way to say total distance. So you're adding up all the distances and dividing it by time. So the total distance divided by total time is your average speed calculation. So new cars nowadays actually can tell you how fast you're going with your average speed in general. So depending on how fast you drive and where you drive, that value can change. Also, just a quick note, notice that there's a symbol right here that means average. So anytime you see this bar, it means average. Quite honestly, I won't use it very often, but you might see it in other readings and textbooks. You might see that measurement. So average velocity, again, we're looking at an average, is going to be a vector quantity because we're going to basically use signs or direction depending on the context of your question. So notice the total displacement over the, the displacement, which is the difference between final and initial, over the change of time right here, so final initial time. Just like I explained in class, Vxi and Ti are usually 0. So officially I like to put this here, but notice it's just going to be Xf over Tf generally as we do this. Now, this is the average velocity, so officially, and let me just be really official here, there should be a line right there to show average velocity. But that's okay, I'll just take that out for a moment. Now, notice that we can actually find an average of velocity if we knew the initial and final velocity, and then divided by 2. This is also an average velocity. So there's two ways we can calculate it. And then if you think about what average velocity means graphically, if this is a velocity versus time graph here, your initial velocity, non-zero, your final velocity, the average just gives you a middle point. So once again, average velocity is kind of, it's helpful, but it's not super informative because notice that your initial velocity and your final velocity are definitely different from what you calculate as average. Instantaneous velocity is basically taking the derivative of a point on a curve. So you might learn this already. It seems like you did in calculus, but it's the velocity at a specific instant. So when you look at your dashboard for your velocity, that's your instantaneous velocity. So another way I like to think about it is a cop, right? A cop will measure your instantaneous velocity. You may have been going 60 miles per hour, but that one moment you're going 85 and they measured that. So again, that's instantaneous velocity. Now, to measure it, you would take the, I have it as a limit right now, which is very true, but it's the instantaneous derivative of a point on a curve. The good news, you don't need to do this in the AP or even in class, but just know the difference between instantaneous velocity and average velocity conceptually. So I like this example because it shows you the difference between average velocity and instantaneous velocity. So here's an animation showing you a car going through a couple stoplights. So actually what you might do, you know, as you drive here to on campus. So notice that if we calculate the average speed of this object, it's, you know, the total distance is 5 miles and it took 0.2 hours. So the average velocity of this car was 25 miles per hour, but hope you noticed that during some points the car actually stopped, right? So there was some instantaneous velocity of 0. So just to give you a heads up on the quality of average velocity, again, it gives you, you know, most of the time this car was going 25 miles per hour, but not all the time. So actually, this is a little, that's okay, you can probably figure it out. I know it's a little blocked off right here. But I actually highly encourage you to do this, because I would do this in class anyway, is pause the video right now and try to solve this first. Now, I want you to do that for a couple reasons. One, you got to practice thinking on your own. So I know that I'll give you some thoughts and help you with your thinking and develop your thinking, but it's very important that you start thinking on your own. This actually might trip you up too, so I actually want you to do that on purpose because it starts asking questions. This is not a typical question, so I want you to be ready for it. And see how far you can get with this, and then of course compare my answers with, you know, the solutions that, compare your answers with my solutions and see what you got. Because there's a lot of learning involved when you do it and when I do it. So I really highly encourage that you do that. So let's pretend that you take a quick pause here, stop the video, read the question, and try to answer the questions. Okay, I'm going to pretend that you did that, and hopefully you did, because it's very valuable for you. So here's an example of average speed and velocity as a calculation. So the black mamba is one of the world's poisonous snakes with a maximum speed of 18 kilometers per hour. It's also the fastest. Suppose the mamba is waiting in a hideout and sees a prey and begins to slither forward with a velocity of 18 kilometers per hour, positive. After 2.5 seconds, the mamba realizes that its prey can move faster than it can. The snake turns around and then slowly returns to its hideout in 12 seconds. Calculate the mamba's average velocity during its return to the hideout. Find the average velocity for the complete trip. And then it says, find the average speed for the complete trip. So, most importantly, when I solve any problem, because there are always going to be word problems, is I like to extract the information out. Once I extract the information out, I like to draw a picture. I kind of do this simultaneously, but just notice that this is what we have. So I'm going to actually start on a new blank page like this. And, And as I extract the information, I'm going to draw it. So here's my snake. There we go. Let's give it a nice little black mamba. So this is a black snake. Color it black. There we go. Give it some nice eyes here. That came out way better than I thought. Not bad. Okay. Okay, so there's our snake. With the maximum speed of that, it's also the fastest. So this just tells us its maximum speed. It doesn't mean it's actually going the speed. So sometimes you're given useful information, sometimes it's not. But it says, suppose it's waiting in a hideout and it sees its prey and begins to slither toward it with a velocity of that. So, coming back to that page, it sees its prey, right? So, let's make a little, I don't know, mouse. Okay, and it's going toward it, so it says the velocity is positive 18 kilometers per hour. So in other words, this thing is moving toward it, so positive meaning toward our mouse here. Okay. After 2.5 seconds, it realizes that it can move faster than it can and turns around and slowly. Okay, so you can see already that I drew this wrong because it says it doesn't actually reach it. Oops, sorry. Because this looks like the guy is moving, so that's okay. You could always change your diagram as you see fit. So it doesn't actually reach the mouse because the mouse can go faster. So let's say it's going this speed for 2.50 seconds. It doesn't actually reach the guy, right? Oops. Sorry, sometimes my computer gets a little bogged down. There we go. Alright, notice I'm also reading this like 3 times. That's very important because you need to understand what's going on. So let's see. After 2.5 seconds, it realizes that it can move faster, then it turns around and goes back to a hideout in 12 seconds. So it takes, you know, sorry for all this. So notice that it goes this way and it takes, their trip takes 2.5 seconds, but then it turns around and goes back and it takes 12 seconds. Now, we don't actually know how fast it's going here, so we don't know the return speed. We just know the their speed and the time, and then we don't know the return speed. And funny, we don't know any distances, so distance is unknown. And it wants us to find the, let's see what it said. The average velocity during the return trip, the average velocity for the complete trip, and the complete speed. So the average velocity is delta x over delta t. But notice that, remember that delta x needs a final position, assuming, that initial is 0. So I need to find distance at some point. It doesn't matter when, but I need to find it. And then, let's see, we also need to find average speed. Again, we do the total distance over the total time here. Okay. So, I'm actually going to skip to the Mama's average velocity for the complete trip. Well, it returns back to its hideout, so no calculation needed for that one. The average velocity for the total trip is actually 0. So that's, well, our meters per second, since it's the same conversion for part B. And I hope that makes sense, because if it's the average velocity, it's going to be the displacement between here and here will be 0. So our average velocity of the entire trip, part B, is 0. You don't need to calculate it, but if you're doing an AP exam, you might want to just explain like it starts and ends in the same position, but 0 is sufficient. So part A. So I got to read the question again. The average velocity during its return hideout. Okay, great. So I don't know the average velocity between the return hideout. In order for me to find that, I need the position. But if you notice the beginning of the hideout, I do have information to find position. So first I'm going to find how far it went. And the way I'm going to do it is to say that the average velocity is going to be delta x over delta t. So I know, actually, before I move forward, notice that this is in seconds and this is in kilometers per hour. I just have to be consistent. It actually doesn't matter if I convert this to hours and then this, and then use that, or convert this to meters per second. It doesn't matter what I do, but I have to be consistent. I'm a creature of habit. I like to go from kilometers per hour to meters per second. So I'm going to actually do that first, just like I did in class. So 1 hour, 3,600 seconds. Told you that this is really handy. And then 1 kilometer is 160934 meters, like that. So, because I managed to not bring my calculator, that was silly. So, what it was, 18 times 160934 divided by 3,600, so 8.05, I'll round it to. 8.05, this is kilometer, I'm sorry, oops, this is meters per second. Okay, that seems about right. And then double checking, just because I'm on video, allow me to just double check that again. 18 times 160934 divided by 3,600. Okay, yeah. Perfect. So this represents my my average velocity during this trip. So that's going to be this number right here. I'm looking for delta x, and my total change in time. So like I said, this is usually 0 because usually I start at 0 time, so 0 time for here, and then it's 2.5 seconds here. So I'm going to shortcut and just write this as 2.05 seconds. That was the duration of time. So, solving this, I have to multiply by 2.05 on both sides. And when I do, solving for x here, I think most of you are comfortable with this. 8.05 times 2.05 gives me 16.5. This is in meters. Very good. Okay. So, 16.5 meters is the distance there. And since we're going the same way back, we can assume that this is also 16.5. So moving on to A, which is the velocity for the return trip. Velocity for the return trip is going to be the following. It's going to be delta x f minus I over the change in time, right? So let's go ahead and do that return. So my initial position is actually over here, right? So my initial position and my final position, so I'm going to call, this is our 0 mark, and this is 16. So my final position is actually 0. My initial is 16.5. And then my time it takes is 12 seconds. So notice that I'm going to get a negative, which hopefully makes sense. I modeled this correctly, right? Because it's actually going toward home. It's going backwards. So let's go ahead and calculate this out. 16.5 divided by 12, 1.37, so 1.38. And that's in meters per second, and this is in fact negative. Please leave that there. So the answer is negative 1.38 meters per second. I could write this as a statement. I could say 1.38 meters per second backwards. Notice that that means the same thing, or back to start, or any of that stuff. So these are all acceptable answers. And of course, it just depends on the context of what the question wants. Does it want this? Does it want that? Does it want both? These are both right, whether you write it like this or like this on an exam. I accept those as correct. We said B was 0. And then C, what was the question for C? Oh, average, I want an average speed. So we need total distance over total time. So with that said, let me go up here. So total distance would be the 16.5 forward, and then the 16.5 backwards. So that's total. And the total time would be the 12 seconds here, and then the 2.5 seconds for the total time. So I'm going to write it mathematically here, because there were two distances and two times. I just wrote them like this. You don't have to do that step, but I'm just being complete here. 16.5 plus 16.5 divided by the time there, which is 2.5 seconds, and then the time back. Let's go ahead and use the calculator. 16.5 plus 16.5. By the way, there's always shortcuts. Take them. It's totally fine. So 33, and then let's do 2.5 plus 12. So we have 33 meters. Again, you don't have to do it as explicitly as I'm doing it. I'm just showing you all my steps. So 33 divided by 14.5. Oops. 14.5. 2.2, I think 8 if I round it, if I saw that correctly. Okay, so that is the final answer. Now, since it's a scalar quantity, no directions needed, we know that the average speed of this object was 2.28 meters per second as we go. So that gives us a general idea that it was going slower most of the time. Notice the 12 seconds, right? This makes this bottom part larger, which makes this number smaller. So it makes sense that this is, you know, smaller than expected because it was mostly taking a long time to go back to start. So generally, if you look at my slides, you'll see that I have the answers there. 12.5. That's always fun. What happened there? 1.05. What did I do there? 1.04. I must have did something. What did I do wrong here? Now that I'm confused. The 16.5, did I convert that wrong? I did. Darn! I converted, this was miles, not kilometers. Okay. The process was right, but let's fix my answers. I'm so sorry, but that's why I put the answers there. Let me just fix this. And, you know, apologize, I made a quick mistake here, but there's 1,000 meters. You probably noticed this in the video. I'm like, stop! Don't do it! Let's fix this. So, I knew that, but that's why I calculated. Do you notice I calculated twice? That's because I knew that it seemed wrong. 1,000, 3,600, 5. Okay. Alright, let's quickly just fix this. Gotta do it right. That's why you get multiple attempts on your homework, because it's something like this. So that becomes 5. This becomes 5. So now that becomes... Now I'm going to do it again just to make sure. So 18, 1 kilometer is 1,000 meters, that makes sense. Divided by 3,600, right? 5, okay. Times 2.05. Or is it 2.05 or 5? Now I gotta check. 2.5, oh man. My apologies about the numbers. 2.5. There we go. I have it written there. I don't even know why I did it that way, so I'm so sorry. Again, you're probably like, don't do it. You're doing it wrong. So 5 times 2.5 is, that's what I thought it was. That's why I was like confused. Perfect. Okay. Alright, so then okay. And obviously you can fast forward this if you're like, I get it. So I'm just changing the answers, as you can see. This is a negative 1.05. That makes a lot more sense. And actually I want you to see me make a mistake, because I just want you to know that I'm not perfect, as you clearly saw, and it's okay to make a mistake as long as you catch it and you learn from it. That's the biggest thing. So actually I don't mind that you saw me make a mistake. I'm not this be-all perfect person. And like you see, you know, a lot of times notice that the mistakes are something like that, right? So they're not these huge mistakes. Obviously, this is a lot of work to fix all the the numbers, but it's not. Let's see, 24. I'm talking now. They're not these dire mistakes. 25. That's what I thought. Okay, and then lastly. 1.72. There we go. Now my answers should match. There we go. 72. 72. Let's make them all match, okay? There we go. Okay. Everything works out okay as long as you use the right numbers. That's really, really helpful, right? Anyway, the point I was going to make is I have the answers down here, so now everything matches the way they should be. And it's okay if your numbers are not exactly, like if you get negative 1.02, it's fine. It's when you get like negative 4, that's totally off, you know. So if they're not totally matching, it's fine. Alright, so now that we did that, let's move on. So about constant motion, okay? So we talked about average speed, so we were assuming an object is moving, you know, with a changing velocity or speed. But when you have a constant motion, that object is obviously maintaining its distance and time. So that's the special condition of constant speed and velocity. So maintain the same distance over time, or and then constant speed is maintaining the same distance, the same speed and the same direction. So I love this example because what you have here, if I go back, is for constant speed. So a car can go constant speed in a circle, right? We can go 25 miles per hour. But this is not constant velocity. In order to maintain constant velocity, I have to go just straight in one direction. So that's the biggest difference, right? So an object that can maintain constant speed could be like a Ferris wheel, assuming, not the starting and the stopping of the Ferris wheel. A train can maintain constant speed. It can go 80 miles per hour on the track, but the track goes all over the place, right? It doesn't keep its direction. And anything that does that really, it could be like, for example, like the Earth around the Sun. That's absolutely maintaining its speed, not its velocity though, because it's definitely changing direction all the time. Circle is by definition a constant change of direction. Things that actually go in a constant velocity, so something that might do that is a falling object. Careful, falling, I'll say terminal velocity. That's not necessarily true. So when you hit terminal velocity, you fall at a constant rate, but you're falling downward. So that's a constant falling. Another thing is maybe like an airplane. If this is like the Earth here, if I'm going from Connecticut to, I don't know, California. This is a beautiful drawing of the Earth, I know. But that would be a constant velocity, going 200 miles per hour during most of the trip. Now, obviously, the start and the stop of the trips are different, so yes, but like during the leg of the trip, it can maintain constant velocity. So those are just some examples of the two. Constant speed can be modeled with this thing called a dot diagram. Like think of a car that leaks, one drop every second. And if it did that, notice that the distance between the dots are the same. So this object is going constant speed. It's maintaining this interval of distance over the same time. And here's a visual, right? So it starts at 0, but in 1 second it goes 10 meters, and then 2 seconds it goes 20, 3 seconds it goes 30, 40, etc. like that. So notice that even though our position's changing, our rate, so rate is a change of time, change over time manages to be the same. So I can describe that rate as a rate. So notice that we're going, we're maintaining the rate of 10 meters per 1 second. And in fact, this rate is called speed. That's exactly what it's doing, right? It's maintaining 10 meters every second. So over time, we can make a prediction, right? So at 9 seconds, just by this rate, I know that we're going to be at 9 meters away, but keeping our speed of 10 meters per second. I don't use this. It's not super common, but I just want to show you that you can use vector diagrams. Now we use an arrow to represent direction, so that makes this a vector diagram. So this is constant velocity because notice the arrows are all the same and pointing the same way. So now this would be constant velocity instead. So take a look at this. So here's a constant speed right here, but look at this one. This one's changing its speed because notice the distance interval is now changing. It's smaller here and bigger here. Take a quick guess. Is this object speeding up or slowing down? And the answer is speeding up because it's going here and then it's going bigger and bigger and bigger distances. Then we're going from bigger distances to small. So this is actually slowing down. So here's your constant velocity here, and here is your changing velocity, which is by definition an acceleration. So anytime you accelerate, both going fast or slowing down, that's an acceleration, you're changing your velocity. we can model constant velocity very nicely on a distance versus time graph. So, the slope of a distance versus time graph is, by definition, velocity, because if you remember from class and in your mathematics class, delta y over delta x, so rise over run. So the change in the rise over the change in the run. Well, like I demonstrated in class, remember that this is actually a position, so distance. Now remember that this x corresponds to that, so not x on a graph, so I know that's a little misleading, but this is the change in distance, and the x measurement of this graph is, in fact, t. So the change in the rise over the change in the run is, by definition, the velocity of an object. And then constant velocity, its characteristic on this graph is a straight line here. Just like that. That's its characteristic, that straight line. Okay, so I think I make a couple points as I go through these slides, so I'll go through it. Oops, wrong button. Okay, so velocity is a vector, so actually the direction of the slant tells us what's going on. This is moving away from start, so this is forward motion, forward constant motion, and this is going back to start, so this is backwards constant motion. So this is forward constant motion, and this is backwards constant motion. So if you were to calculate the slope of this, the slope is, in fact, negative mathematically, and the slope of this would be positive, just like you would expect. The shape of the graph tells you which one's faster. You're, of course, getting a reference point. So if you're going graph B right here, and you have your speed like this, but notice that this one is steeper. The steeper it is, the faster it becomes, because you're covering more distance in less time. So, let's see. Okay. I'm just seeing where I'm getting here. So the steepness of the graph, how steep the slope is, tells you the order of how fast it is. Now, of course, we're comparing here, so you need something to compare with, but just by looking at this, A is definitely faster than B. And then what kind of motion is this? Take a guess. A horizontal line on a distance versus time graph is rest. Because notice that here's your position, and you're not changing your position over time. So when you see this, this is an object at rest. And just like that. So just by looking at our constant motion graph, we can get that piece of information. Alright, so again, this is one of those things where I think you should do it first before I do it. But here we go. Let's draw the graphs for this. So an object remaining at rest would look like this. That would be A. And then moving, honestly, can be anything that's not this. Like literally anything. I'm just going to draw this. But honestly, you could have drawn this. You could have actually drawn this. It just can't be horizontal because the word of moving, and that's why there can be multiple solutions. Moving slow would be a shallow line, and moving fast would be a steep line. Positive direction would be this way, and negative direction. Now, it doesn't matter where I start here, actually, because I could actually do this, which is a little silly because it's small, but I don't have to start at the origin and end at the origin every time. So, in fact, another solution to this exact question could be the following. I could actually start here and do this. This just means my initial position is no longer 0. And same thing, I can actually start here, and although this is not extended, I could do this from the negative direction. Right? Although you're like, what does this mean? Not only am I going backwards, but I'm going behind where I started. So these are options too that you can use. I just want to see where I'm going with this. Okay, that's that. So I'm actually going to skip this question for now and show you here's that same example plotted on a graph. So notice that if I were to plot this on a graph, it does make your straight line. So constant motion is a straight line at a distance versus time graph, just like that. So does this object ever move constant motion? Sure, it does. You look for straight lines. So just to show you really quick, I would say from like here to about here. I would say this interval is constant motion between 1 and maybe 2 1/4. And then I would say that anytime looking for a straight line, so I would say from here to about here. So about 3 1/4 to 4 is constant motion. This is what objects typically do, right? They might like speed up and then move constantly and then change direction, and you have to slow down and change direction. So actually any of these little peaks right here are stopping points, because notice that the instantaneous slope with that is actually 0, so it stops down there. And then there's my picture's blocking this, but notice that that's also a constant speed right there. So A, B, and then C if you continue that down. So there are places where this object does move constant. The curves, which I didn't really talk about, always are your accelerated motion. I mean, I'm going to go into that in more detail in our class, our next class, but that here are different, these curves will represent acceleration. So curves are acceleration, straight lines are constant motion on a distance versus time graph. So very specific. Curves equal acceleration, straight lines equal constant motion. Okay, we talked about this already. Very good. Oops, my computer is stuck. Okay. Alright, so the next thing I wanted to talk about is velocity. That's a little different here. I just want to see where my slide's going. Okay. A velocity versus time graph is different from a distance versus time. You have to completely erase them for your... Everything I just taught is different now for velocity graphs. So it's very important that you read and watch. I don't know why my pen is not working right now. I think it's because it's might be dying. So anyway, you have to watch this. This is very important. So if I were to model constant motion on a velocity graph, well, it has to be a straight line. It's not going to be straight because I'm drawing it, but you get the idea. Now, think about what that means. For velocity, I have to maintain a velocity, right? So in order for me to maintain my velocity, it has to be a straight line. In fact, it doesn't matter where the straight line is, it just has to be straight. In fact, with no acceleration, notice that from here to here, from 0 to any positive value, that anything in this region is moving forward. And anything in this region is moving backwards because of the negative sign. So notice that number 1 here is constant velocity moving forward. But this one is constant velocity moving faster, right? Because number 1, this number is going to be less than number 2 right here. So this is actually moving much faster than this. This is moving pretty fast in the negative direction. This is moving slower in the negative direction, but still moving constant because we have a horizontal line. And then, if you're on the line, if you're on this line, the 0 line, it means you're not moving, right? Because you don't have a velocity during that time. So straight lines on a velocity versus time graph means it's constant velocity. Closer to the x-axis is slower. 0 means Zero velocity means you're not moving. It happens at the x-axis. And remember, negative doesn't mean lesser. In fact, 3 is actually pretty fast moving as opposed to 4. And actually, if these were in the same positions, let's pretend that they are, they would be moving the same speed but different directions. So, you can do a lot of things. As you can saw, motion can be described in different lengths and time. You have speed and displacement. You have distance and velocity, although, of course, let's organize them in terms of length. The length has displacement and distance. Motion has speed and velocity. There's average speed and constant speed. Constant speed is when you keep your motion, you keep your distance and time intervals the same. And you can model constant speed in a velocity versus time graph and a distance versus time graph. So for constant speed and a distance versus time graph, looks like a slanted line, but for a velocity versus time graph, it looks like a straight line, and both of these are constant. Just like that. So next class, we're going to look at objects that change their speed and their velocity, as known as acceleration, and our first lab is going to be measuring acceleration. And this concludes our video. Let me know if you have any questions.